Welcome back to the course of Applied Elasticity. In today's lecture, we will continue with our discussion for the torsion problems. In the previous lecture, we had started our discussion on the torsion problem. We had a quick recap on the simple theory of torsion and then started discussion on the Sand-Venance theory of torsion which is valid for the non-circular cross section. These can be solved using the Prandtl stress function approach, which we had discussed in details. So, phi xy being a Prandtl stress function, this must satisfy two conditions. One is Laplacian of phi is equals to minus 2 g theta. This condition should be satisfied by the Prandtl stress function over the entire domain, over the entire cross section, where theta is the angle of twist per unit length of the bar and g is the modulus of rigidity or shear modulus. So, this is the first condition to be satisfied by the chosen Prandtl stress function, and second condition which Prandtl stress function should satisfy is phi equals to 0. Actually, it should be phi equals to constant, and for the singly connected boundary, means for solid shafts which is only having outer boundary, we choose that constant to be 0. So, phi equals to 0 is the second constraint which should be satisfied by the Prandtl stress function phi over the outer boundary. So, first condition should be satisfied over total domain for all values of x and y over the entire cross section, whereas second one must be satisfied only along the outer boundary, only along this boundary curve. Now, non-zero stress components tau xz and tau yz were defined with respect to the stress function phi as tau xz is del phi del y, tau yz is minus del phi del x, and the relation between torque and theta was obtained like this. The torque acting is equals to area integral of twice of the Prandtl stress function. Now, for solving any torsion problem of prismatic bar with non-circular cross section, our first objective or first goal is to choose a proper Prandtl stress function phi xy which satisfy both the condition, that is Laplacian of phi equals to minus 2 g theta over entire domain and phi equals to 0 over the outer boundary. Then with respect to phi, we can obtain the non-zero shear stress components, we can find out the point at which the maximum shear stress is generated, and finally, we can find out the amount of torque in terms of that stress function, which would basically give us a T theta relation between the applied torque and resulting angle of twist. Now, we will take different cross sections, different non-circular cross section. In today's lecture, we are going to start with an elliptic cross section bar. So, we are going to consider a prismatic bar with a cross section being ellipse and will apply this Prandtl stress function approach for solving the torsion problem of that elliptical bar. So, torsion of an elliptical bar which we are trying to solve. Our aim is to get the stress distribution and also find out the torque T and angle of twist theta relation between them. So, let us consider this cross section. An elliptical cross section is considered for the prismatic bar which is subjected to end torque T. The cross section is constant or uniform along the z axis. Along the length, cross section is not varying. So, it is independent of z. 2a is the total major axis. So, semi major axis length is taken as a, semi minor axis length is taken as b. So, total minor axis is 2b for this chosen ellipse. Now, the equation of this elliptic boundary, equation of this curve we can write as x square by a square plus y square by b square equals to 1. This is the standard equation describing the elliptical boundaries or elliptic curve, x square by a square plus y square by b square equals to 1, where a is the length of the semi major axis, b is the length of the semi minor axis. Now, based on this, we are going to choose our Prandtl stress function. And for this ellipse, the total cross sectional area, the formula for cross sectional area for an ellipse is equals to pi times AB. Total area is pi times semi major axis length times semi minor axis length. Pi AB is equals to total cross sectional area capital A. Now we are going for our choice of stress function. Now what are the conditions the stress function phi should satisfy? Del 2 phi or Laplacian of phi is minus 2 g theta over total domain. This is one condition. For all values of x and y, this should be satisfied, and phi equals to 0 along boundary. Now the initial choice of phi or Prandtl stress function is always with respect to or starts with the help of the second condition. We must have phi to be 0 along the boundary, and how is boundary defined? Boundary is defined by this ellipse equation, x square by a square plus y square by b square is equals to 1, and hence we can choose our stress function of this particular form, some unknown constant m times x square by a square plus y square by b square minus 1, and you can see as this x square by a square plus y square by b square equals to 1 along the boundary. If you substitute that here, immediately this term goes to 0. So phi equals to 0 along the boundary. This second condition is automatically satisfied if you are going with a choice of phi like this. So always for the Prandtl stress function approach, the stress function is chosen like some unknown constant m times the equation of the outer boundary of the given cross section. That will satisfy the second condition, phi equals to 0 along the boundary automatically. So with this we are starting our solution. Our Prandtl stress function phi is m times x square by a square plus y square by b square minus 1, where m is some unknown constant which we need to determine, and that will be obtained with the help of this first boundary condition. So if you replace phi here in the first condition over entire domain, Laplacian of phi is equals to minus 2 g theta. Replacing phi there, we will be getting some idea what should be the value of m. Now moving forward, substituting this phi in the Laplacian condition, Laplacian of phi is equals to minus 2 g theta. We are substituting this phi here and finding its Laplacian. So Laplacian in the Cartesian coordinate is del 2 phi del x2 plus del 2 phi del y2, and here that should be equals to minus 2 g theta. Now if you start from the given phi, del phi del x, what will that be? That will be 2 m x by a square, and then del 2 phi del x2 will be, I think, 2 m by a square. Similarly, we can substitute this del 2 phi del x2 as 2 m by a square, and similarly del 2 phi del y2, that can be obtained as 2 m by b square. So substituting those here, we will be getting left hand side as 2 m times within bracket 1 by a square plus 1 by b square, and that should be equals to minus 2 g theta. Now a, b are known quantities, so we can write m in terms of a, b as minus g theta a square b square divided by a square plus b square. So we got the expression for this unknown constant m, and this equation of m we can replace here in the expression of the Prandtl stress function phi, and can write the complete Prandtl stress function phi as minus m is replaced with g theta a square b square divided by a square plus b square times this equation of ellipse, that is x square by a square plus y square by b square minus y. So this is the total Prandtl stress function which is required to be used for solving the torsion problem of the prismatic bars with elliptical cross section, with A being semi major axis length and B being semi minor axis length. G is modulus of rigidity, theta is angle of twist per unit length. So we have obtained an expression for phi or Prandtl stress function which satisfy both the condition. One is Laplacian of phi is minus 2 g theta, that is satisfied, and also phi equals to 0 over the boundary, that is satisfied due to presence of this ellipse equation. Over the boundary this part would go to 0. So, phi will be 0 over the boundary. So, hence this Prandtl stress function satisfies both the conditions. Now, if I plot that, now if I plot this Prandtl stress function over x and y, here you can see over the boundary, elliptic boundary, I have plotted phi for different set of values of x and y. Now, all these are equations of ellipse. You can see as you keep on choosing different values of x and y, you will be getting the stress function contours. So, all these ellipses are stress function contours. For each of these ellipse, phi is constant. So, let us say here phi equals to phi 1, which is a constant. If you take another one, let us say slightly on the inner side, there phi is equals to another constant phi 2. So, all these elliptic lines are basically the stress contours. Phi is set to different constant values and all those stress function contours are basically ellipse. So, you can see the set of concentric ellipses starting from outer boundary and shrinking towards the center, and note that at the outer boundary phi should be 0. So, on the outer boundary, let us say that is phi equals to phi naught, phi 0 and should be 0. And as you are going towards the inner side, the value of phi should increase, the stress function contour value will increase, that you can see by looking at the color codes here. So, blue side colors are closer to 0, on the outer boundary values are on the lesser side, which are referring to the referred with the blue contours. As you are going towards the center, the values are increasing and the color is shifting towards the red zone. So, the stress function value is increasing on the stress function contour near the center. So, this is the plot of the stress function, pictorial representation of the stress function contour across the elliptical cross sections. Now, moving forward to the torque acting on the elliptical bar, we had derived the equation of torque in terms of Prandtl stress function as T is equals to twice area integral of phi. Phi xy is the Prandtl stress function, which for the present problem of elliptic cross section is obtained like this. So, we will replace this expression of phi here and we will try to obtain the relation between applied torque T and theta. You can see phi is function of theta, the angle of twist. If I replace phi within the integral, then right hand side will have theta and then some integral of x and y over the entire domain, and left hand side is torque. So, this equation will give us a relation between the applied torque and resulted angle of twist. So, substituting this phi in the integration T and keeping that minus g theta a square b square by a square plus b square, this constant term out of the integral, we will be having that 2 minus 2 times that constant g theta a square b square by a square plus b square, then area integral of only this part, which is function of x and y. So, x square by a square plus y square by b square minus 1 area integral. This is nothing but the equation of ellipse. Now, if you try to recall the properties of this any area, what is double integral or area integral x square dx dy and what is area integral y square dx dy? These are nothing but the 2 second moments of area I y y and I x x. So, we can write this x square dx dy is equals to I y y and y square dx dy integral is I x x, and last term the integral of dx dy is total area. So, this term is double integral x square dx dy divided by a square. Now, double integral x square dx dy over the total area is nothing but I y y. By definition of the second moment of area about the y axis, this numerator is I y y. So, this is I y y by a square, that is written here. Similarly, the second term integral area integral y square dx dy will be I x x, that divided by b square, and last term is area integral dx dy, which is total area. So, we can remove the integral and write this t as the constant times I y y by a square plus I x x by b square minus a. Now, for the elliptical cross section, the I y y is equals to pi a cube b by 4, I x x is equals to pi a b cube by 4, and total area capital A is pi a b. So, for any ellipse with semi major axis length small a, semi minor axis length small b, we can write I x x, I y y and total area A using these standard formulas. Now, I am going to replace all those forms in this equation of t. If I do so, capital T will be like this, where I y y is written as pi a cube b by 4, I x x is written as pi a b cube by 4, and area capital A is written as pi a b. Now, we can simplify the term within the bracket. These a square will get cancelled and this b square will cancel. So, we will be having pi a b by 4 plus pi a b by 4 minus pi a b. So, this would be minus pi a b by 2. Multiplying this with the external constant, in total t would be becoming pi g theta a cube b cube divided by a square plus b square. So, this is the torque and the angle of twist theta relation. T is pi g theta a cube b cube divided by a square plus b square for the elliptical cross section. Now, if you recall about the simple theory of torsion, theta was defined as T by Gj. So, angle of twist is normally written as torque divided by modulus of rigidity times J, where J was known as polar moment of area. So, from here you can think T is equals to G theta J. Now, here in this particular elliptic cross section, this was valid for the circular cross section. This is for circular bar from the simple theory of torsion. Now, if I compare that, here let us say T is equals to G theta J prime, where J prime is pi a cube b cube divided by a square plus b square. Now, if I am comparing this Saint-Venant's theory of torsion torque theta relation with the simple theory of torsion torque theta relation, then we can define a quantity J prime which is known as effective polar second moment of area, and that is equals to pi a cube b cube divided by a square plus b square. That we are simply deriving by defining a expression of this T equals to G theta J prime, where J prime should be this. But this is not the actual polar second moment of area of the elliptic cross section, because effective polar second moment of area is obtained by from this torque T theta relation based on Saint-Venant's theory, but from the properties of area, the true or the actual polar second moment of area for the ellipse is equals to J is pi a b by 4 divided by a square plus b square. This is simply summation of I x x and I y y. By definition, whatever I x x and I y y we had, if you sum them up, you will be getting the actual polar second moment of area of this elliptic cross section. Now, you can see this J is not equals to J prime for ellipse. So, thus the simple theory of torsion is not valid. If you try to use this formula, we will end up with a wrong result, but for circle that should be same. Now, let us verify that. How can we verify? For the circle, we must have A equals to B. If you impose A equals to B, both J and J prime would come out to be same as pi a to the power 4 by 2. Imposing A equals to B in this equation of J, also in this equation of J prime, you will be getting both J and J prime as pi a to the power 4 by 2, and thus for the circular bar T is G theta J, which is equals to G theta J prime. valid for both the Saint-Venant's theory as well as the simple theory of torsion. So, this is a validation by using this or by reducing the elliptic cross section to circular cross section, we can verify that our Saint-Venant's theory is matching with the result given from the simple theory of torsion. Now, moving forward to the shear stress components, the non-zero stress components tau xz and tau yz, which are generated due to application of this torque T, were defined in terms of Prandtl stress function phi as tau xz is del phi del y, tau yz is minus del phi del x, where phi we had obtained, T and theta relation also we had obtained. Now, replacing this stress function in these expressions del phi del y and minus del phi del x, and then simplifying it further, we will be getting tau xz as minus 2 g theta a square y by a square plus b square, and tau yz as 2 g theta b square x by a square plus b square. So, at any x and y, if you replace the values of x and y in these two equation, at any particular point we can get both the stress components tau yz and tau xz. These are only two non-zero stress components, all rest are 0. So, putting these values of x and y at any point within the domain within the ellipse, we can find out the stress distribution using these two equations. And in terms of t, if you are writing this equation in terms of t, these would be like tau xz is minus 2 t y by pi a b cube and tau yz is 2 t x by pi a cube b. So, this is obtained by using this t theta relation. So, here you can write theta in terms of t, and thus writing theta in terms of t, this equation tau xz and tau yz in terms of applied torque T can be obtained. Now, finding the resultant shear stress, the total shear or resultant shear acting at any point P will be the square root of summation of square of tau xz and tau yz. So, thus this resultant shear tau at any point within the elliptic cross section is square root of tau xz square plus tau yz square. Substituting tau xz and tau yz in terms of these equations, we can write the resultant shear stress as 2 t by pi a b root of x square by a to the power 4 plus y square by b to the power 4, where x is varying between minus a 2 plus a, y is varying between minus b 2 plus b. Now, we are interested to find out the maximum value of the shear stress, the point at which this shear stress would be maximum. Now, x can vary between minus a 2 plus a, y can vary between minus b 2 plus b. We also know for any torsion problem, the maximum shear stress occurs at the boundary, on the outer boundary. Now, outer boundary is having 4 critical points, 2 endpoints of the same major axis, 2 endpoints of the minor axis. These are the 4 points where there is a possibility of having the maximum shear. Now, the endpoints of the same of the major axis are defined like a comma 0 minus a comma 0. Endpoints of the minor axis are defined like 0 comma b, 0 comma minus b. Now, if you check the value of tau at all these 4 points and compare them, as a greater than b, we can clearly see that maximum shear stress is going to occur at x equals to 0, y equals to plus minus b, that is at this point and at this point. These are the points corresponding to the maximum shear stress. At the end points of the minor axis, we are going to get the maximum shear stress. So, tau max, which is tau at 0 comma plus minus b, can be obtained as 2 t divided by pi a b square. The value of the tau at 2 endpoints of the major axis will be lesser than this. Hence, all the 4 endpoints of the major and minor axis are not critical points as long as the maximum shear stress is concerned. Only the endpoints of the minor axis will be the critical point corresponding to maximum shear stress, and that shear stress value is 2 t divided by pi a b square for this elliptic cross section. Now, moving to the displacement formulation of torsion, we had discussed about the torque theta relationship and stress. Now, we are interested to find out the displacement, how the body is deforming with this Saint Venant's theory of torsion for non-circular cross section. So, displacement fields were assumed like this: u is equals to minus theta y z, v is theta x z, and w is some w function of x y. So, this is some unknown function, and this is not equals to 0 for non-circular cross sections as warping is allowed for the non-circular sections. Now, using this, if you obtain the strain fields and stress fields, we will be getting 4 stress components to be 0. This we had already discussed: sigma xx, sigma yy, sigma zz, tau xy. These 4 are 0 stresses. Only 2 non-zero stresses are tau xz and tau yz, which can be written in terms of corresponding strain or then corresponding displacement components as tau xz is equals to g times del u del z plus del w del x, and tau yz is g times del v del z plus del w del y. These are obtained using the simple strain displacement relations. Now, replacing these u, v and w here in these two equations, you will be getting tau xz as g times del w del x minus theta y, tau yz as g times del w del y plus theta x. And note that w is function of x and y only, independent of z. Now, coming to the equilibrium equation, for the torsion problem we were left with only one equilibrium equation to be satisfied, that we had discussed in the previous lecture. So, that equilibrium equation in absence of any body force is del tau xz del x plus del tau yz del y. Now, if I replace tau xz with this and tau yz with this in these two equations, equilibrium equation, and simplify it, it would be having only two terms, del 2 w del x2 plus del 2 w del y2 equals to 0, means Laplacian of w is 0. So, this is the governing equation over the out of plane displacement component w. This must be non-zero for non-circular cross section. Laplacian of w equals to 0. So, instead of using phi, the stress function, we can also solve the problem by using this displacement formulation. This is also called warping function approach. W is directly proportional to the warping function. Theta times warping function psi is equals to W. So, if Laplacian of W is 0, Laplacian of warping function is also 0. This is the alternate approach of Saint Venant's theory of torsion for non-circular cross section. Now, let us apply this for the elliptical cross section, the problem which we are discussing in this lecture. So, we know the expressions of tau xz, tau yz in terms of t. Here, for displacement formulation, we will avoid phi. Stress function is not involved. We will try to solve for w in the displacement formulation. So, tau xz, tau yz resultant shear stresses were already obtained in terms of applied torque, and torque theta relation is also known, which are written here. So, using the obtained torque theta relation, we can express theta, the angle of twist per unit length, in terms of t as theta equals to t times a square plus b square divided by pi g a cube b cube. Now, writing the non-zero stress components in terms of w, as discussed in the previous slide, tau xz is equals to g times del w del x minus theta y, tau yz is g times del w del y plus theta x, and in terms of t we know these two expressions of tau xz, tau yz. Now, we are going to compare these two, and also this particular theta is replaced by using this theta t relationship. So, if you replace this theta here, obtain the tau xz, tau yz, these two big expression, and then compare these two equations with the previously obtained expressions of tau xz and tau yz. From that, from the first equation tau xz, you can write del w del x as a function of t applied torque. From the second equation of tau yz, you can write del w del y as function of applied torque as this. Del W del x will be T times b square minus a square times y by pi g a cube b cube, and del W del y would be T times a square minus b square times x divided by pi g a cube b cube. Now, combining these two, we got the partial derivative of out of plane displacement component W with respect to x and y. If I combine these two and then integrate it, that would result the solution of W, which will come out to be T times b square minus a square x y divided by pi g a cube b cube. The integration constant is set to be 0 because at the center 0 point the displacement should be 0. At somewhere at one of the end we will be having 0 displacement at the boundary. So, keeping that center point to be non-moving at x 0, y 0, w is 0, we can get rid of the integration constant, and this will be the function of w. You can see w is proportional to x y, it is also directly proportional to t. So, this is the solution for the displacement formulation for torsion of elliptic bars, and if you check this w in the Laplacian equation, you can substitute this w here and check that this obtained w satisfies the Laplacian equation, that is the governing differential equation for displacement formulation of the torsion. Now, plotting this w, that is displacement contours across the elliptic cross section, you will be getting a plot like this. So, similar to the stress function contour, here I am plotting the displacement contours. Now, this total elliptic cross section is divided into 4 quadrants like this. This is along positive x, this is along positive y. Now, you note that for the values of for different quadrants, you will be getting the different set of value or different signs of w. If x and y both are positive, then this quantity x y to be positive, that is in the first quadrant, that is first quadrant. On this side both x and y are positive. Now, b is smaller than a, so b square minus a square term would be negative, which will result this w to be negative in the first quadrant. Similarly, if you keep on checking, w is positive in the second quadrant, w is negative in the third quadrant, and w is once again positive in the fourth quadrant. So, 1/4 of the cross section is going inside, then second quadrant 1/4 of the cross section is coming out, third quadrant going inside similar to first quadrant, fourth quadrant is once again coming out similar to second quadrant. You can see the color code for second and for first and third, you are having blue region which is negative warping, those cross sectional points are going inside the plane. For second and fourth, that is coming out, and this clearly shows the warping of the cross section. So, some part of the elliptic cross section is coming out, some part is going in, and this shows the distortion of the cross section for this non-circular elliptic bar. So, in this lecture we had discussed about the torsion of an elliptic bar using both stress function approach and displacement formulation approach. We had obtained the expression of maximum stress which occurs at the two endpoint of the minor axis, and we had also obtained the torque and angle of twist relation. Thank you.